Welcome, learners, to another deep dive. Today, we're taking a shortcut, getting you well-informed about the really fascinating world of physical techniques in inorganic chemistry.
That's right. We're pulling back the curtain on the tools chemists use every day to understand, well, the very building blocks of our world.
Exactly. How atoms are arranged, how molecules react, all that fundamental stuff.
Our mission today is really to distill the essential insights from Chapter 8 of Shriver and Atkins Inorganic Chemistry, the 5th edition. This chapter introduces the most important physical techniques used to investigate atomic and electronic structures.
And also how they study reactions, right?
Absolutely. Think of it as a guide to this scientific detective work that reveals the secrets of matter at the tiniest scales.
We'll explore a whole range of methods from, shining X-rays on crystals to zapping samples with lasers, all designed to give us a peek at what's really going on at the molecular level.
And the goal is to explain each technique, what it measures, and why it matters, all without needing any visuals. So you can really picture these intricate processes in your mind.
Okay, let's dive in. First up, diffraction methods. These sound absolutely paramount for determining structures.
They really are. Diffraction fundamentally relies on the interference of waves when they encounter an object. Simple as that, conceptually.
Okay.
For crystalline solids, where you have atoms arranged periodically like soldiers on parade, if you shine radiation with a wavelength similar to the atomic spacing,
Like X-rays.
like X-rays, exactly, you get a diffraction pattern, a unique scatter.
And the big one here is X-ray diffraction, XRD. So how does that work?
Okay, so X-rays are scattered by the electrons in atoms, those electron clouds. When these scattered waves coming off different atoms interfere constructively.
Meaning they add up.
They add up, yeah. They produce these intensity maxima, or reflections, bright spots in the pattern. And this is beautifully captured by Bragg's equation.
Ah, yes. Bragg's law, second sin theta equals n lambda.
That's the one. Here, d is the spacing between parallel planes of atoms in the crystal, theta is the angle that X-rays hit at, it is just an integer, and lambda is the X-ray wavelength.
So by measuring the angles and intensities of these reflections,
We get incredibly precise information about atom positions, bond lengths, bond angles, the whole geometric picture. It's powerful stuff.
and you mentioned the scattering is by electrons. Does that mean some atoms scatter more strongly?
Exactly. The intensity of scattering is proportional to the square of the number of electrons. So atoms rich in electrons dominate the pattern.
So like lead hydroxide would give a really strong signal compared to the oxygen or hydrogen.
Precisely. The lead atom's many electrons just stand out much more clearly in the data.
Okay, the chapter mentions two main X-ray techniques, powder and single crystal. Let's start with powder XRD.
Right. In powder XRD, you don't need a perfect crystal. You use a polycrystalline sample, basically finely ground powder, with lots of tiny crystallites all pointing in random directions.
So the X-ray beam hits these random orientations.
And it scatters in all directions, forming these cones of diffraction at the specific angles predicted by Bragg's equation for that material.
And a detector scans these cones.
Yep. It stands around and measures the intensity at different angles, producing a pattern, a unique pattern for that crystalline substance.
Like a fingerprint for identifying materials, right?
Exactly like fingerprint. It's used all the time for phase identification, checking if you made what you thought you made, checking sample purity, determining lattice parameters.
Can you give an example?
Sure, like identifying different forms or polymorphs of titanium dioxide, say anatase versus rutile in white paint. They have the same formula, TiO2, but different crystal structures, so different powder patterns.
Okay. And what about this Rietveld method?
Ah, that's a more advanced analysis for powder data. It involves fitting a calculated diffraction pattern to the experimental data to refine structural details. It's good, but generally less precise for atomic positions than single crystal.
Which brings us to single crystal X-ray diffraction, the gold standard.
Absolutely, the gold standard for full structure determination. Here you need a single well-formed crystal. Doesn't have to be huge, maybe tens of micrometers or larger sometimes.
And modern machines are fast.
Incredibly fast. Modern diffractometers use things like image plates or CCD detectors to collect thousands of reflections very quickly. A skilled crystallographer can sometimes solve the structure of a small inorganic molecule in, well, under an hour.
Wow. Defining bond lengths down to fractions of a picometer.
That's the level of precision we're talking about. It's amazing.
But I remember reading something about hydrogen atoms being tricky.
Ah, yes. That's a key limitation of X-rays. Hydrogen atoms only have one electron, so they scatter X-rays very weakly. It's hard to pinpoint their positions accurately, especially if there are heavy atoms around hogging the scattering signal.
So X-rays aren't perfect for everything.
No technique is. That's why we need a toolkit. And for hydrogens, that's where neutron diffraction often comes in. We often visualize these structures using ORTEP diagrams too, which show atoms as ellipsoids representing thermal motion.
Before we get to neutrons, what about those huge synchrotron sources?
Right, synchrotrons. They generate much more intense X-ray beams than lab sources. Way, way brighter.
You can study tougher samples.
Exactly. Much smaller crystals, more complex structures like massive proteins or enzymes, and you collect data much faster. They're usually national or international facilities because they're so big and expensive.
Okay, so back to the hydrogen problem. If X-rays struggle with light atoms, how do neutrons help?
Well, neutrons are different. They aren't scattered by electrons. They interact with the atomic nuclei.
Ah, the nucleus itself.
Yes. And the strength of that interaction doesn't depend simply on the number of protons or electrons. So neutrons are highly effective for locating light atoms like hydrogen, lithium, even oxygen, especially when they're next to heavy metal atoms where X-rays would just see the metal.
That sounds like a crucial complement, a really important pairing with X-rays.
It absolutely is. It also lets you distinguish between elements that are neighbors on the periodic table or have similar numbers of electrons, like, say, oxygen and nitrogen.
Yeah.
They might look similar to X-rays, but they scatter neutrons very differently.
But neutron facilities are rarer.
Much rarer, yeah. They usually require a nuclear reactor or a spallation source, so it's a more specialized but very powerful technique.
Okay, moving on from scattering waves off atoms. Many techniques involve the absorption of electromagnetic radiation.
Yes, these absorption methods give us information about a compound's energy levels, electronic energy levels, vibrational levels, and they can be quantitative too.
Like measuring concentration.
Exactly. The whole electromagnetic spectrum, from high-energy gamma rays down to low-energy radio waves, probes different energy transitions in molecules. Ionization, vibration, rotation, even nuclear spin flips.
And the timescale matters too.
Absolutely. Different techniques provide snapshots over different timescales. IR spectroscopy sees vibrations which are super fast, like picoseconds. NMR looks at nuclear spins, which is much slower, milliseconds. So they see different average pictures of a molecule if it's moving or changing shape.
Let's start with one many people might know. Ultraviolet visible, or UV-vis spectroscopy. What's its core principle?
UV-vis looks at the absorption of ultraviolet and visible light. This energy excites electrons, specifically valence electrons, bumping them up to higher energy levels or orbitals.
Okay. And it's widely used in inorganic chemistry.
Very widely. We measure the intensity of absorption as something called absorbance A. It's defined logarithmically. Log of the incident light intensity divided by the transmitted light intensity, I0 over I.
And this connects to the classic Beer-Lambert law.
Precisely. A equals epsilon times J times L, where epsilon is the molar absorption coefficient, a measure of how strongly the substance absorbs light at that wavelength. J is the molar concentration, and L is the path length of the light through the sample.
So that's the key link between how much light is absorbed and how much stuff is there.
Exactly. It's fundamental for quantitative analysis, like monitoring how fast a reaction is proceeding by watching a reactant disappear or a product appear, or determining equilibrium constants.
And the color we see is related to what's absorbed, right? What we don't see tells us what we do see.
An excellent way to put it. The color we perceive is the complementary color to the light that's absorbed. If a compound absorbs blue light strongly, it appears yellow to us.
Can we track reactions with it?
Definitely. You can watch spectral features change over time. Sometimes you see isospecific points. These are specific wavelengths where two interconverting species happen to have the exact same molar absorption coefficient.
What does that tell you?
If you see sharp isospecific points, it's strong evidence that you have a clean conversion of just one species into another, with no stable intermediates building up. And for really fast reactions, you can use techniques like stopped flow mixing coupled with UVV detection.
Okay, now let's talk about molecular wiggles. Infrared, IR, and Raman spectroscopy.
Right, these are our windows into molecular vibrations. They characterize compounds by how their bonds stretch and bend, giving us insight into bond strength, bond order, and even molecular shape.
You mentioned a bond acting like a spring?
Kind of, yeah. Its vibrational frequency, or energy, depends on its stiffness, the force constant, and the effective mass of the atoms involved in the vibration. We usually talk about these energies in units of wave number, inverse centimeters.
And how many ways can a molecule vibrate? It feels like it could get complicated.
It can. For a nonlinear molecule with n atoms, there are 3n-6 fundamental ways it can vibrate, called normal modes. For a linear molecule, it's 3n-5.
But not all vibrations show up in both IR and Raman.
Correct. There are selection rules. Only modes that cause a change in the molecule's overall electric dipole moment are IR active. And only modes that cause a change in the molecule's polarizability, how easily its electron cloud is distorted, are Raman active.
Polarizability, like how squishy the electron cloud is.
That's a good analogy, yeah. How easily it gets pushed around by an electric field.
And they're often complementary techniques.
Very much so. Especially for molecules with a center of inversion, like a square planar molecule or an octahedral one. For those, there's the exclusion rule. A vibration cannot be both IR and Raman active. If it shows up in one, it won't show up in the other.
That sounds really useful for structure determination.
It is. The classic example is SEF4 xenon tetrafluoride. When they measured its IR and Raman spectra, there were no common absorption energies. That immediately told them it must have a center of symmetry pointing strongly towards the square planar geometry, not something like tetrahedral.
What are some other key applications?
Oh, tons. Determining molecular shapes, like distinguishing square pyramidal from trigonal bipyramidal structures for an AX5 molecule, just by counting the number of IR and Raman active stretching bands. They are incredibly important for identifying functional groups.
Like carbonyls and metal complexes?
Exactly. Metal carbonyls are a huge area. The CO stretching frequency is very sensitive to the electron density being pushed from the metal onto the CO ligand via backbonding. It tells you about the electronic environment and can even distinguish terminal CO ligands from bridging ones, which vibrate at lower frequencies.
And modern IR is fast.
Yeah, Fourier transform IR, FTIR, allows rapid data acquisition. You can get a full spectrum in seconds, which opens the door to kinetic studies, following reactions in real time.
Okay, let's shift gears again. Resonance techniques. These sound like they involve tuning things just right.
They do. These techniques bring energy level separations, often tiny ones influenced by magnetic fields, into resonance with electromagnetic radiation of a specific frequency.
They leverage magnetic properties.
Yes, either the magnetic properties of certain nuclei or the magnetic properties of unpaired electrons.
And the absolute powerhouse here, particularly for chemists working on solutions, has to be nuclear magnetic resonance, NMR.
Oh, absolutely. NMR is indispensable for structure determination. It works because nuclei with non-zero spin, like the proton 1H, carbon-13, phosphorus-31, fluorine-19, act like tiny magnets.
When you put them in a strong external magnetic field.
They align either with or against the field, creating discrete nuclear spin energy levels. Then we apply radiofrequency radiation, think radio waves, and if the energy matches the gap between these levels, the nuclei absorb it and flip their spin state. This absorption is what we detect.
And the exact frequency needed depends on the nucleus and the field strength.
Yes, the energy separation is proportional to the applied magnetic field strength, and a property of the nucleus called its magnet-to-gyric ratio.
Okay, but the really useful part is the chemical shift, isn't it?
That's where the structural information comes in. The chemical shift is the slight difference between the resonance frequency of a specific nucleus in your sample molecule and the frequency of a standard reference compound, usually tetramethylsilane, TMS.
Why the difference?
It's because the electrons circulating around a nucleus create their own tiny local magnetic field that usually opposes the main applied field. So the nucleus feels a slightly different effective field depending on its electronic environment. This shielding or deshielding causes the shift.
So different chemical environments give different shifts.
Exactly. It's measured in parts per million ppm to be independent of the spectrometer's field strength. It tells you about the local magnetic environment, the functional group, the oxidation state. Incredibly informative.
What about spin-spin coupling? That sounds like nuclei talking to each other.
It basically is. Spin-spin coupling reveals connectivity. The spin state of one magnetic nucleus influences the magnetic field felt by a nearby nucleus, but the effect is transmitted through the bonding electrons.
Okay.
This interaction splits the NMR signal of the affected nucleus into a multiplet, a pattern of lines. The spacing between these lines is the coupling constant, J, measured in Hertz. It doesn't depend on the field strength, only on the interaction strength, which usually decreases as the number of bonds between the nuclei increases.
And the pattern tells you how many neighbors it has.
Pretty much. For a spin-12 nucleus coupled to n-equivalent spin-12 nuclei, its signal splits into n+1 lines. For instance, in the 19F NMR of chlorine trifluoride, ClF3,
Which has that T-ship.
right, the two axial fluorines are equivalent, and they see the one equatorial fluorine, so their signal is split into a doublet, 1+1 lines. The equatorial fluorine sees the two equivalent axial fluorines, so its signal is split into a triplet, 2+1 lines. That doublet-triplet pattern is direct proof of the structure.
NMR isn't just static structure, though, right? What about molecular dynamics?
Ah, yes, fluxionality. This is where NMR's timescale becomes really interesting. NMR operates on a millisecond timescale, which is much slower than IR's picosecond timescale.
So it sees an average picture if things are moving fast.
Exactly. If parts of a molecule are interchanging positions faster than the NMR timescale, NMR sees an average signal. A classic example is iron pentacarbonyl, SCO5. It has a trigonal bipyramidal structure with distinct axial and equatorial CO ligands.
But NMR sees them as equivalent.
At room temperature, yes, because they interchange positions rapidly via a process called Berry-Sutter rotation. NMR sees just one signal for all 5 COs, but IR, being much faster, can distinguish the axial and equatorial CO stretches.
Can you slow it down?
You can. By cooling the sample, you slow down the interconversion. Eventually, you can reach a temperature where the exchange is slow on the NMR timescale, and you resolve separate signals for the axial and equatorial environments. You can even measure the energy barrier for the process. It's like having a variable speed camera for molecular motion.
Can you do NMR on solids, too?
Yes, solid-state NMR is a powerful technique, though it faces challenges. In solids, anisotropic interactions, things that depend on the molecule's orientation relative to the magnetic field, usually cause very broad, uninformative signals.
So how do you get sharp signals?
The trick is magic angle spinning, or MAS. You spin the solid sample very rapidly, like tens of thousands of times per second, at a specific angle, the magic angle, about 54.7 degrees relative to the magnetic field. This rapid spinning effectively averages out those broadening anisotropic interactions.
And that gives sharp lines again.
Dramatically sharper lines. Techniques like CPMAS NMR combine this with other tricks and have been crucial for studying materials like zeolites, catalysts, polymers, even looking at fluxionality in the solid state.
Okay, if NMR is for magnetic nuclei, what about unpaired electrons? Is there a technique for them?
There certainly is. That's electron paramagnetic resonance, EPR, also sometimes called electron spin resonance, ESR.
So this is for paramagnetic species.
Exactly. It's the go-to technique for studying species with one or more unpaired electrons. Think free radicals, transition metal complexes, metals in metalloenzymes, anything paramagnetic.
How does it work? Is it similar to NMR?
The principle is very similar. An unpaired electron has spin 12, creating a magnetic moment. In an external magnetic field, this electron spin can align either with or against the field, giving 2 energy states.
And you use radiation to cause transitions.
Yes, but because the electron's magnetic moment is much larger than a nucleus's, the energy gap is much bigger. We use microwave radiation, typically around 9 gigahertz for standard X-band spectrometers, to cause transitions between these electron spin states.
Instead of radio waves like NMR. And what's a G value in EPR?
The G value is analogous to the chemical shift in NMR. For a totally free electron, the G value is about 2.0023, but inside a molecule, interactions between the electron spin and its orbital angular momentum spin-orbit coupling shift this G value.
Does it tell you about the environment?
Yes, the G value is sensitive to the electron's environment. It can also be anisotropic, meaning its value depends on the orientation of the molecule relative to the magnetic field. Often we cool samples way down to liquid nitrogen or even liquid helium temperatures to slow down relaxation processes and get sharper spectra.
And is there coupling in EPR like in NMR?
Yes, there is. It's called hyperfine coupling. This is when the electron spin interacts with the magnetic moments of nearby nuclei that have spin, like 1H14N, 31P, or even metal nuclei.
What does that do to the spectrum?
It splits the main EPR line into multiple lines. If the electron couples to a nucleus with spin I, the line splits into 2I plus 1 lines of equal intensity. If it couples to ligand nuclei, it's often called superhyperfine coupling. This provides incredibly valuable information about where the unpaired electron density is located, how much it's shared onto ligands, basically, the degree of covalency in metal-ligand bonds.
Okay, one more resonance technique. Mössbauer spectroscopy. This sounds a bit more exotic. What's the Mössbauer effect?
It is a bit more specialized, yes. The Mössbauer effect refers to the recoilless absorption and emission of gamma rays by a nucleus embedded in a solid lattice. It relies on extremely precise energy matching between the source emitting the gamma ray and the sample absorbing it.
Recoilless, like the nucleus doesn't get pushed back when it emits or absorbs the gamma ray.
Exactly. In a solid lattice, the recoil momentum is essentially taken up by the whole crystal, so the energy of the gamma ray isn't lost to recoil, allowing for this incredibly sharp resonance.
What kind of nucleus do you need?
It only works for certain isotopes. The most famous and widely used is iron 57, 57Fe. There's a radioactive source, usually cobalt-57, which decays to an excited state of iron 57, 57Fe. This 57Fe then emits a gamma ray.
And your sample needs to contain iron 57.
Yes, the sample needs stable 57Fe. It can then resonantly absorb that gamma ray, but only if its nuclear energy levels are almost perfectly identical to those in the source.
How do you achieve that perfect match? Or rather, how do you probe slight differences?
By using the Doppler effect, we move the radioactive source relative to the sample at very slow speeds, just a few millimeters per second. This movement causes a tiny shift in the gamma ray frequency due to the Doppler effect.
So you scan the velocity.
Right. The Mössbauer spectrum plots the gamma ray absorption as a function of the source velocity. Peaks appear at velocities where the Doppler-shifted gamma ray energy exactly matches an allowed nuclear transition in the sample.
What kind of information does this give?
Two key parameters. First, the isomer shift. This is the overall shift of the absorption peaks relative to a standard reference, like metallic iron. It's very sensitive to the s-electron density at the nucleus.
So it can tell you about oxidation states.
Yes. For example, it can readily distinguish between Fet2 and Fe states because they have different numbers of d electrons which shield the s electrons differently, changing the density at the nucleus. It can also give clues about covalency versus ionicity.
And the second parameter?
That's quadrupole splitting. The excited state of 57F has a non-spherical charge distribution, a quadrupole moment. If the nucleus sits in an environment with an asymmetric electric field gradient, meaning the surrounding electrons aren't spherically distributed, this gradient interacts with the quadrupole moment and splits the nuclear energy level.
So a single absorption peak might split into two.
Exactly, a doublet. The magnitude of this splitting tells you about the symmetry of the electronic environment around the iron nucleus. So Mössbauer is incredibly powerful for studying iron in minerals, oxides, catalysts, alloys, and even biological systems like hemoglobin.
Okay, moving from resonance to techniques that sound a bit more energetic. Ionization-based techniques, kicking out electrons and fragments.
That's a good way to think about it. These techniques involve bombarding a sample with high-energy radiation or particles, and then measuring the energies of the electrons or molecular fragments that get ejected.
Let's start with photoelectron spectroscopy. PES.
Okay, PES works by irradiating a sample, usually with UV light or X-rays, causing electrons to be ejected. These are the photoelectrons. We then measure the kinetic energy, EK, of these ejected electrons very precisely.
How does that relate to the electron's energy inside the molecule?
There's a simple relationship based on energy conservation.
Yeah.
The kinetic energy of the photoelectron equals the energy of the incoming photon, H times nu, minus the ionization energy, EI, of the electron, EK HEN nu, I. The ionization energy is how tightly bound the electron was in its orbital.
And Koopman's theorem.
Koopman's theorem provides a useful, though approximate, link. It states that the ionization energy of an electron from an orbital is roughly equal to the negative of that orbital's energy, calculated theoretically.
So PES lets us map out the energy levels of orbitals.
Essentially, yes. It gives us direct experimental access to orbital energies. There are two main flavors, XPS and UPS.
XPS.
X-ray photoelectron spectroscopy. It uses higher energy X-rays to eject core electrons from inner shells. Because core electron energies are characteristic of each element, XPS tells you which elements are present, often on the surface of a material. It can also give information about oxidation states from small shifts in core level energies. It's sometimes called ESCA, electron spectroscopy, for chemical analysis.
And UPS.
Ultraviolet photoelectron spectroscopy. It uses lower energy UV light to probe the valence shell electrons, the ones involved in bonding. UPS generally has much higher energy resolution than XPS.
So you can see more detail.
Yes, often you can resolve vibrational fine structure on the photoelectron peaks. If ejecting an electron excites vibrations in the resulting ion, it tells you that the electron came from a bonding or antibonding orbital because its removal changed the bond strength. Non-bonding electrons usually give sharp peaks with little vibrational structure.
Fascinating. Now, X-ray absorption spectroscopy, XAS. This sounds related to XPS and maybe even XRD.
It is related. XAS involves tuning the energy of an X-ray beam across an energy range where core electrons can be excited or ionized. This is called an absorption edge. Instead of measuring ejected electrons like XPS, XAS measures how much the X-rays are absorbed by the sample as a function of energy.
So you scan the X-ray energy.
Exactly. Different features in the absorption spectrum near and above the edge provide different kinds of information.
Like the pre-edge region.
Right. Just below the main edge, you might see small peaks corresponding to exciting a core electron into empty valence orbitals. The position and intensity of these pre-edge features can tell you about the oxidation state and coordination geometry of the absorbing atom.
And just above the edge.
That's the XAS region X-ray absorption near-edge structure. This part is very sensitive to the oxidation state and the local coordination environment. It often acts like a fingerprint for a specific chemical site. There's also NXFS, near-edge X-ray absorption fine structure, which is particularly useful for studying molecules absorbed on surfaces, as it can tell you about their orientation.
And further out, XAFS.
Extended X-ray absorption fine structure. This refers to the weaker oscillations in absorption that occur at energies well above the edge. These oscillations arise because the ejected photoelectron wave gets scattered by neighboring atoms.
Like ripples bouncing off nearby objects.
Precisely. The outgoing and backscattered waves interfere, creating this oscillatory pattern in the absorption. By analyzing the frequency and amplitude of these EXAFS oscillations, you can determine the type, number, and distances of the atoms surrounding the absorbing atom.
Even in disordered materials.
Yes. That's a major strength of EXAFS. It doesn't require crystalline samples. You can get local structural information around a specific element, even in amorphous materials, solutions, or complex biological samples.
Okay, one more ionization technique. Mass spectrometry. We talked about weighing molecules before.
We did. Mass spectrometry measures the mass-to-charge ratio of gaseous ions. It's incredibly versatile and widely used, but it is a destructive technique. The sample gets consumed.
And the main challenge is making those gas phase ions.
Yes, especially for compounds that aren't naturally volatile or are fragile. There are many ionization methods. Electron impact, EI, works well for small, robust molecules. It hits them with high-energy electrons. Fast atom bombardment, FAB, uses high-energy atoms. MALDI matrix-assisted laser desorption ionization is great for large molecules like polymers. You embed the sample in a matrix that absorbs laser light.
And ESI.
Electrospray ionization. This is huge, especially for biochemists and inorganic chemists working with ions or polar molecules in solution. You spray the solution through a charged needle, creating tiny charged droplets. As the solvent evaporates, the ions are released into the gas phase. It's very gentle.
Once you have the ions, how are they separated?
Several ways. Magnetic sectors bend the paths of ions based on their millage time of flight, TOFs. Analyzers measure how long it takes ions to travel a fixed distance. Lighter ions get there faster. Ion cyclotron resonance, ICR, traps ions in magnetic fields and measures their cyclotron frequency, which is MELS dependent, offering very high resolution.
And the spectrum shows peaks at different mass-to-charge ratios.
Correct. You look for the molecular ion peak corresponding to the intact molecule, usually minus an electron or plus a proton, depending on the method. But you also see fragment ions where the molecule broke apart during ionization. These fragmentation patterns can be like a fingerprint to help identify the structure.
And isotopes show up clearly.
Very clearly. As we mentioned with chlorine earlier, the relative abundances of natural isotopes create characteristic peak clusters. Boron has 10B and 11B, bromine has 79 Br and 81 Br in roughly equal amounts. These isotopic patterns are invaluable for confirming elemental composition. And high-resolution mass spec can measure masses so accurately it can distinguish between molecules with the same nominal mass but different exact masses, like 12C16O, mass 27.9949, and 14N2, mass 28.0061.
Okay, let's shift to some fundamental chemical analysis techniques, just figuring out what elements are present and how much.
The bedrock of characterization, really.
Atomic absorption spectroscopy, AS. How does that work for elemental determination?
AAS is conceptually similar to UVVs, but instead of molecules in solution, the absorbing species are free atoms, usually in a gas phase created by a flame or a graphite furnace.
And atoms have sharp absorption lines.
Very sharp, characteristic electronic transitions. The key is using a special light source called a hollow cathode lamp. This lamp contains the specific element you want to measure, and it emits light only at the exact wavelengths that element absorbs.
So you need a different lamp for each element.
Generally, yes. You shine the light from, say, a copper lamp through your atomized sample. If copper atoms are present in the sample, they will absorb that specific light. The amount of light absorbed, the reduction in intensity, is directly proportional to the concentration of copper atoms in the sample.
How sensitive is it?
Very sensitive. Especially with graphite furnace atomization, GFAAS, you can reach detection limits down to parts per billion, or even parts per trillion for many metals. Almost every metallic element can be determined this way.
Okay, another classic. CHN analysis for carbon, hydrogen, and nitrogen.
A workhorse technique. You take a tiny, precisely weighed amount of your sample and combust it completely at high temperature, around 900 degrees C, in a stream of pure oxygen.
What does that produce?
All the carbon becomes CO2, all the hydrogen becomes H2O, and the nitrogen becomes N2 gas, possibly with some nitrogen oxides, NH.
Then you measure those gases.
Yes. The mixture of gases is swept by a carrier gas, usually helium, through a reduction furnace containing hot copper. This removes any excess oxygen and converts any excess oxygen and converts any anoxics back to N2. Then the gases pass through a series of detectors, often thermal conductivity detectors, which sequentially measure the amounts of H2O, CO2, and N2.
And from that, you get the percentages.
Exactly. The instrument calculates the mass percentages of C, H, and N in the original sample. This is absolutely critical for determining or confirming the empirical formula of a new compound, like checking if your synthesized ferrocene really is C10H, 10Fe.
What about X-ray fluorescence, XRF? That also sounds like elemental analysis using X-rays.
It is, but it works differently from XRD or XPS. In XRF, you bombard the sample with high-energy X-rays, energetic enough to knock out core electrons from the atoms in the sample.
Creating vacancies.
Yes. Then electrons from higher energy levels drop down to fill these core-level vacancies. When an electron drops down, it releases energy in the form of another X-ray photon.
And these emitted X-rays are characteristic.
Precisely. The energy or wavelength of this emitted fluorescent X-ray is characteristic of the element from which it originated because it depends on the specific energy level differences in that atom. By analyzing the energy spectrum of these emitted X-rays, you can identify which elements are present and, by the intensity, how much of each.
What elements does it work for?
It's generally great for most elements heavier than about sodium, so Z greater than maybe 8 or 10. It's widely used in geology, materials science, archaeology. It's also the principle behind the energy dispersive X-ray analysis, EDAX or EDS systems, often found on electron microscopes.
Lastly, thermal analysis. Watching what happens when you heat things up.
Right. This includes several related techniques.
Like TGA.
Thermogravimetric analysis, TGA, which we touched on. It measures the change in mass of a sample as its temperature is increased, usually at a constant rate. Fantastic for seeing things like dehydration, decomposition, desorption, oxidation, anything involving a mass change. The stepwise dehydration of copper sulfate pentahydrate is a classic TGA experiment.
What about DTA and DSC?
Differential thermal analysis, DTA, and differential scanning calorimetry, DSC. These measure energy changes, not mass changes. In DTA, you heat your sample and an inert reference material side by side at the same rate and measure the temperature difference between them.
So if the sample undergoes a process,
If the sample undergoes an exothermic process, gives off heat like crystallization, it gets temporarily hotter than the reference. If it undergoes an endothermic process, absorbs heat like melting, it gets temporarily cooler. This shows up as peaks in the DTA curve.
then DSC.
DSC is similar but more quantitative. It works by adjusting the power supplied to the heaters for the sample and reference to keep them at the same temperature. It measures the difference in power needed to maintain this equality.
So the peak area is directly related to enthalpy change.
Exactly. DSC gives more reliable quantitative enthalpy data for transitions like melting, boiling, phase changes, or chemical reactions. Both DTA and DSC are great for identifying materials by their characteristic transition temperatures, fingerprinting, and measuring heats of transition.
The chapter also briefly mentions a few others: magnetometry, electrochemistry, computational methods.
Just briefly, yes. Magnetometry techniques like using a Gauss balance, VSM, or a SQUID magnetometer measure how strongly a material is attracted or repelled by a magnetic field. This tells you about the number of unpaired electrons and the overall magnetic moment.
Electrochemistry.
Techniques like cyclic voltammetry measure electrical currents that flow when a species is oxidized or reduced at an electrode surface as you vary the potential. It reveals redox potentials, information about reaction mechanisms, and stability.
And computation.
Computational chemistry is huge now. Using methods ranging from ab initio calculations, based purely on quantum mechanics, to semi-empirical methods, which use some experimental parameters, to density functional theory, DFT, we can model structures, energies, reaction pathways, charge distributions, spectra. It's an incredibly powerful complement to experimental work, though the accuracy always depends on the level of theory and the system being studied.
Wow, okay. From X-rays mapping atoms with incredible precision to lasers probing vibrations, magnetic fields tickling nuclei, and computations modeling behavior. It's clear that inorganic chemists have just an incredibly diverse and powerful toolkit.
It truly is remarkable. We've explored how diffraction methods like X-ray and neutron scattering reveal atomic arrangements, how various absorption spectroscopies, UVVs, IR, Raman probe electronic transitions, and molecular vibrations.
And how resonance techniques like NMR, EPR, and Mössbauer delve into the subtle magnetic properties of nuclei and electrons, giving really detailed local information.
We also touched upon those ionization-based methods like PE and XAS that reveal orbital energies and local structure, and mass spectrometry for nailing down molecular masses and formulas.
And rounded it out with those essential chemical analysis techniques, AS, CHN, XRF, thermal analysis, that tell us about elemental composition and how materials transform.
And the key takeaway really is that each technique offers a unique window, a different perspective. Often, it's only by combining several of these approaches, fitting the pieces together, that we can truly build a comprehensive understanding of a compound's structure, its properties, and how it behaves.
So what does this all mean? It means our ability to design new catalysts, create better batteries, understand metallones in our bodies, develop advanced materials. It all hinges on using this fundamental toolkit wisely.
Absolutely. And the continuous innovation in these physical techniques themselves keeps pushing the boundaries, allowing us to see more detail, study more complex systems, and ask questions we couldn't even frame before.
Thank you for joining us on this deep dive. We hope you feel more informed about how chemists see the molecular world, and maybe a little inspired to look deeper into the molecules that make up everything around us.
From the entire Deep Dive team, thank you for tuning in.